Bismillahirrahmanirrahim. Assalamu alaikum dear students. In previous two lectures we have studied about nucleophilic substitution reaction, but in previous lectures we studied about SN2 reactions, and we talk about the class of organic functionalities that we can produce by using alkyl halides. Then we studied about different nucleophiles, their specificity and effect of solvent, and further we studied about nucleophiles and their nucleophilicity and comparison of nucleophiles in aqueous media and in gas phase. So this is a second type of nucleophilic substitution reaction that was named as SN1 reactions. As we studied in previous lecture, that kinetics of nucleophilic substitution reaction was studied by a group of scientists at University College London during 1930, and specifically they studied about the rate of reaction. Simply we can say that about the kinetics of reaction. So in previous lecture we studied that tertiary alkyl halides, they give too slow reaction by mechanism of SN2. It means their reaction is too slow to measure if we talk about SN2 reaction. But practically, when we involve these reactions in nucleophilic substitution, they successfully replace their halide group by nucleophile. So it means they are being subjected by nucleophilic substitution reaction, but the mechanism is not SN2. For SN2 reactions, we studied that rate of reaction is dependent upon nucleophile as substrate as well as on nucleophile. But here the scenario is different. The rate of reaction is just directly proportional to concentration of tertiary alkyl halides. So it means if we increase the concentration of tertiary alkyl halide, the reaction will go in forward direction, but if we increase the concentration of water, there will be no change in rate of reaction. So this reaction depends only on the concentration of tertiary alkyl halides. That's why these reactions are called as first order reactions. So if we talk about the mechanism of these reactions, the mechanism of this reaction is composed of three steps. At first stage, this alkyl halide dissociates into a carbocation. So here is tertiary alkyl halide. In the presence of aqueous media, the bond between carbon and halide dissociates, and the product is a carbocation. So at this stage, very important thing that we have to know is the geometry and hybridization of this reactant and this product. Here the carbon is sp3 hybridized and its geometry is tetrahedral. After losing one of its group, it just containing three groups, three bonds. So when carbon is attached to three groups, so its geometry transforms from tetrahedral to trigonal, planar, and hybridization also transforms from sp3 to sp2. In case of SN2 reactions, we studied that the reaction undergoes just one step. At one step only, at one side there is a bond development between attacking nucleophile and carbon, and from the other side the bond starts to to break between carbon and nucleophile, and we obtain exactly inversion of configuration. But here we have an intermediate. Intermediate has a trigonal planar geometry. So this trigonal planar geometry provides equal opportunity to the nucleophile to attack on its front face as well as from the back side. So in these type of reactions, we will obtain a racemic mixture. It means 50% of the molecule will retain the original geometry configuration of the reactant, and 50% of the molecule will be rearranging in opposite direction. So here is step 1. At step 2, water molecule will approach this carbocation. Here is a positive charge. So water molecule will attack on this carbon. So it has equal opportunity to attack on the front, and similarly this water molecule can attack from the back side of this carbon, planar carbon geometry, and consequently we shall obtain another species that is called as alkyl oxonium ion. So this oxygen, which is actually sharing its electron pair to this positively charged carbon, this will get a positive charge. So these two steps are included in the mechanism of SN1 reaction. So the rest of the reaction that I am going to write, the third step of this reaction, that is not actually the part of nucleophilic substitution reaction. The third step is just acid-base reaction that just removes this hydrogen from this species to make it a stable alcohol. So step 3, I am going to write at the bottom, there is alkyl oxonium there is a positive charge on this oxygen, and other water molecule will obstruct this hydrogen atom, and this bond will provide electron pair to this oxygen, and in the product side we shall receive an alcohol and H3O positive. So if we go back to the overall reaction, in overall reaction we can see there is 1 mole of tertiary alkyl halide, there are 2 moles of water, and in the product we are getting an alcohol, hydronium ion, and a bromide anion. So this reaction proceeds by first order mechanism because the rate of reaction is only dependent on the concentration of tertiary alkyl halides. By increasing or decreasing the concentration of water, there will be no effect on the yield of this product. So how this reaction proceeds? There are total 3 steps to accomplish this reaction, but step 1 and step 2 are included in the mechanism of SN1 reaction. The third step is just an acid-base step that just transforms this alkyl oxonium ion into a neutral alcohol. Initially, the bond between carbon and bromide will slowly broken up, and we shall obtain a trigonal planar carbocation. This planar geometry provides equal opportunity to attacking nucleophile. Nucleophile can attack from the front as well as from the back side. So just to represent you, I am writing down the other species that can be produced during this reaction. This kind of species will be produced and 50% second kind of species will produce. So these reactions are stereospecific reactions. In these reactions, we can obtain 50% if the reactants containing R configuration. So 50% of the molecule will be having R configuration and 50% of the molecules will be with the S configuration. So why tertiary alkyl halides undergo SN1 reaction mechanism instead of SN2 reaction mechanism? The reason behind this reaction mechanism is the stability of carbocation. As we know that the inductive effect of methyl group is donating. So there are three methyl groups which provide electron density to this formally positively charged carbon. So that's why tertiary carbocation is highly stable intermediate. In previous lectures, we discussed about two terms. One of them was transition state and the other one is intermediate. When a reaction is happening, so a reactant or a combination of reactants, we have reactant 1 and reactant 2. So when these two reactants combine, means they collide with each other. So there will be two modes of collision. One is effective and the other one is ineffective. So when there is effective collision between two reactants, they will transform into an activated complex. This activated complex, by following certain number of species, will transform or broken up into products. This activated complex may be categorized into two classes. One of them is transition state and the other one is intermediate. So how can we distinguish between which species is transition state and which species is intermediate? If the species at this stage can be identified by any chemical test, by any spectroscopic analysis, so that kind of species will be named as intermediate. So if there is no clue, no evidence about the existence of that species, so that hypothetical species will be named as transition state. So if we compare the reaction mechanism of SN1 and SN2, so we can say that when a reactant follows SN2 reaction mechanism, so there will be a development of transition state between two reactants. But when two reactants undergo SN1 reaction, they will have a specific intermediate. This intermediate has stability, so this can be identified by different chemical and spectrochemical tests. So that's why this activated complex is known as reactive intermediate. So we can have three kind of intermediates. One is this tertiary carbocation, and other kind of carbocation that can be produced during this reaction may be secondary carbocation, means carbon is connected to two methyl groups. The third class will be primary carbocation. In secondary carbocation, we have two methyl groups. In primary carbocation, we have one methyl group. So, in previous classes, we have studied about the stability of carbocations. A tertiary carbocation has most stability, then secondary, and then primary. The reason behind this is that in tertiary carbocation there are three methyl groups which are donating electron density to this carbocation. In secondary carbocation there are two methyl groups, and in primary carbocation there is only one methyl group. The stability of carbocation depends upon the number of methyl groups connected to that particular carbon atom. So here we have a comparison of different alkyl halides and their rate of reaction. We can see the methyl bromide has a rate of reaction about 0.6. Then there is ethyl bromide. This is unsubstituted carbon. This carbon has further one methyl group. So after the development of carbocation, there is one methyl group to donate electron density to this carbon. Here there is no carbon to donate electron density. In case of isopropyl bromide, when this bromide will transform into carbocation, we have to write here methyl groups. So there will be a secondary carbocation, and in the last one we shall obtain a tertiary carbocation, and we can see the rate of this tertiary carbocation to undergo SN1 reaction is around 10 million. So simply we can conclude that most of the time the primary alkyl halides, they will undergo SN2, and tertiary alkyl halides, they will undergo SN1. So for secondary alkyl halide, there are multiple factors which will decide the fate of substrate. They can either go by SN2 reaction, they can either go by SN1. It depends upon attacking nucleophile as well as on the solvent. In the coming lecture, we shall talk about the reactivity of secondary alkyl halides. The conclusion is that primary alkyl halide will follow SN2 reactions, secondary alkyl halides will undergo SN1 reactions. Further, in SN2 reactions, there is transition state. In SN1 reaction, there is a intermediate. In SN2 reaction, there is 100% inversion of configuration. In SN1 reaction, there is 50% retention and 50% inversion. Because the intermediate in case of SN1 reaction is a planar sp2 hybridized carbon that provide equal opportunity to attacking nucleophile that can attack from the front and also from the back side. So now we are going to discuss about energy profile diagram of SN1 reaction mechanism. So initially we have a mixture of tertiary alkyl halide in aqueous media. So there is a tertiary alkyl bromide. So as we studied in the mechanism, that at first step the bond between carbon and halogen starts to break. So whenever there is a bond development or bond breakup, so the energy of species will increase. And thus both of these species are present or together, means the species present in aqueous media. So at first step the bond between carbon and bromine will broken up, and we shall obtain a tertiary carbocation and a bromide, and both of these two species are present in aqueous media. So we can say that from here to here, this is a completion of first step. So this first step is also rate determining step. This is also known as slow step. So when this carbocation will be produced, will be developed in aqueous media, so water molecule will start approaching to this positively charged carbon. Again, whenever there is a bond development, the energy of species will increase. From here, we can see the species are neutral, their energy is low. When their bond starts to break, energy will go to higher level. When the bond is broken, the energy is down. Further, when there is bond development, the energy will increase. So after the settlement of this bond development, the energy will again decrease and we shall obtain alkyl oxonium ion. So this bond, this species is not stable because oxygen is carrying positive charge. So water molecule present in the media will start approaching this positively charged oxygen, and again the bond between this oxygen and hydrogen will be in transition state, and bond between water and hydrogen will start developing. So when this bond will completely develop, the energy of this species will be decreased. Overall, we can see the energy of reactant is higher as compared to product. So we can connect these species by graphical representation. So we can see the energy is increasing, decreasing, and ultimately the product have lowest energy. So this is called as energy profile diagram. So this is too much complicated diagram as compared to SN2 reaction mechanism. In SN2 mechanism, we studied just the reactant, the transition state, and the product. So sometimes this energy profile diagram is included as a long question. So you have to keep in mind that from here to here is step 1. This is slow step. This is also called as rate determining step. And this is step 2, and these all steps are just a simple acid base reactions, and this is a fast step. So actually this part is not considered as part of SN1, SN2 reaction mechanism. Sorry, SN1 reaction mechanism. But if I ask you to develop energy profile diagram for SN1 reaction, so you have to draw it completely. You have to produce this final product, which is a tertiary butyl alcohol.